Welcome everyone to our presentation. We're TeamOutScope conducting the Automated Warehouse Inventory Scheme project with Schaeffler Company as our client. Our team's members are Hoàng, Thắng, Phương, and Amzai. This project is supervised by our mentor, Mr. Linh. At Schaeffler Company, the daily operation is subjected to manual labor. They have to operate bulky vehicles to maneuver alongside 47 meters aisles of 10 meters high pallet. It can be seen in the following figure. The current situation poses several problems, from human error caused by fatigue from repetitive process to large time and power consumption, which affects the company's total expense per day. Among the problems, Schaeffler raises the need for a solution to one of the key targets, stock accuracy. These solutions must have to help the company to perform weekly to monthly cycle stock count with minimal manual effort, while ensuring the physical location of the stock matches with the record on the management system. Therefore, having spent our time discussing with the company, we come up with a scheme consisting of the hardware prototypes and a software system to be integrated into the current warehouse management system. The following chart depicts the requirement analysis. The hardware prototypes comprises of a car navigating back and forth along x-axis and a drone navigating up and down along z-axis. Meanwhile, the software system would be of an image processing tool to recognize the inventory's identity and a website user interface as management monitor. The scenario for a complete checking process follows a sequence. The cars carry the drone to a location for the drone to navigate up to the inventories requested by user using website. Via an equipped camera, the drone captures the identity, then sends to the system to confirm the accuracy before returning to the initial position on the car. During the journey, the car must continually supply power for the drone. Having done the analysis on the requirement, we started conducting researches on the reviews to the current technology's applications. Please pay attention to the red circle object. They are the AR marker for the drone to track the landing position on the car. Besides, for the car to perform obstacle avoidance, we use LiDAR sensor to map the warehouse. With respect to the software side, Flip-based enterprise existing solution is an example for the features we can consider to incorporate into our system. This concludes our researches as we are capable of developing our own solution. We will be using the unmanned system technology, which consists of the hardware and the software system. In the following few slides, Hoàng would help us to illustrate the hardware system. Hoàng, can you please continue?
Hello everyone, I'm Hoàng and now I'm going to present to you about the hardware system. So firstly, is the design approach of a car in a hardware system. This is the model of a car on the CAD software with the visualization of a component in the car. As you can see, that the car has 3 levels. The bottom level is including the first head controller motor, printed circuit board, DC motor, and light follower sensor. And the middle level has a second head module, lead acid battery, buck converter module, safety switch, and an Arduino Mega at the main processing unit. And at the top level is including the JSON nano, GPS module, and the LiDAR sensor. And component position is suitable for scanning and connection. Next is the prototype and manual control function of the car. At the simulation, the behavior of the car in the phase A of the project. At phase B, we implemented the car and began the testing. This is a final prototype of the car. After finishing programming and assembly back together, we begin to test the behavior of the car. The following short video is demonstrate the car for forward and backward movement. As you can see that the car moves forward and backwards smoothly. Next is the slam and automation function on the car. And the following picture is the slam function is implemented on the car. And the environment surrounding the car is visualized and plotted at the map with a blue square on the map represent the car to keep track their location. And to do the function path landing and navigation, the 2D navigation goal function will guide the car to the right location on the map. You can see it is located on the grass plot in the picture. And then now moving to the drone. So this picture is also capture the model of the drone in the CAD software. As you can see that it also has 3 levels. At the bottom level, we will have the inventory ID capture camera, Raspberry Pi, battery case, IR marker, checking Pi camera. And at the middle level, we have a power distribution board, radio receiver, PR, barcode scanner module, and at the top level is including the brushless motor, propeller, and propeller guard, electronic speed circuit, and lastly the flight controller at the main processing unit on the road. So this is the prototype of the car and the drone after finishing the project that on the CAD software. And now is moving to the drone, the true prototype of the drone. You can see that after configuration, important sensor, main processing unit in the firmware, we call that the X4. We begin to test the function of the drone, and this video will demonstrate that how to manual control the drone to test it. And as you can see, is that the drone can fly up from 5 to 6 meters to it, and that's how we can manual control the drone to test the function, the behavior of the drone. Now moving to the automation concept on the drone. First on that the drone is simulation on the gazebo environment to see how the main processing unit communicate with the Raspberry Pi 4. Following the picture, the diagram, and the MAC link communication is the main protocol. Besides that, the Raspberry Pi 4 can send the data of the state of the drone to the ground station, with running the X4 firmware in another computer by UDP port in the same local network. And the same method of communication is used with the real prototype hardware by following the picture. You see that the X4 HITL here is represent the main hardware. Will communicate with the other part of software by a MAC link protocol. So that is all about information about the hardware system, and Phương will continue to present about the software system.
From phase A, our group used the WebSocket protocol to implement. However, in this semester, after the ROS research and implementation, we will substitute it into a third-party software which is pusher to a more secure and faster way. Another change is the decentralization of the database. So the new software architecture is as follows. Starting from the website where we host it on Heroku, user can access it anywhere as long as they have the right username and password. Now to handle the real-time communication and instant update on the website, we use a cloud channel which will push and receive the information passed into it. The database that we use is MongoDB. Then in a real-time update for the drone and cars such as the status like battery, current location, altitude, such things like that, most of these would use the ROS environment, and this would create a launch file that can be put into the startup. So within every 10 seconds, the ROS publisher publishes the data to the cloud channel, and with the respective channel, the website can take that data and display it correspondingly into the website. So now when the user searches for the location, the car would receive it first and go to the respective location such as Rec 3, column 3. And the car would inform the drone that it has done its job. So now when the drone received it, it would fly up and then do some barcode scanning and check back to the information it has received. When it is the right match, It will change the state to take pictures and save the best quality pictures to the local folder and then inform the Node.js server here that it is done. Then the server will post this picture along with the location to the database. Now on the left, which is the website, it would have the database listening string. So whenever a picture is inserted, the changes can have an instant update on the website. Since Frost, publisher or subscriber would execute content continuously, therefore a finished state machine is a must to handle every stage during the process. This can be easier to understand in the demo. So now it is where the OpenCV is applied to detect QR of barcode and the AR marker. So the QR of barcode would be executed into the camera at the front of the drone, while the AR marker would be the PI camera installed at the bottom of the drone. As there is a ventilation at the top of each rack in the factory, and the drone flying calibration can be shaky, this would dramatically affect the camera capture. Therefore, OpenCV is also applied to detect blurriness, and this can help to get the best image quality before inserting into the database. Now my colleague Tang will take over and continue to talk about the project progress.
Thank you, Phương. Next is a summary of what we have accomplished after 2 semesters. Regarding the hardware, the present model of the car is fully built with attached components. The car's hardware process was kept at 90%, as the accuracy of the tasks in the automated process need to be improved. With respect to the drone, the mechanical process is 19% complete. Due to the unmounted part on the prototype, which has a negative impact on the proper application of the PID controller, as well as the automation implementation. Hence, its hardware progress was at 85%, since only successful communication with the ground station was implemented. Regarding the software side, the back-end and front-end design categories were already in the algorithms testing phase, completing 100% out of the scopes. From the complete UI for the website, the information and data could be updated regularly based on changes in the database collection using the MongoDB data stream. For us, the communication between user, car, and drone was mostly finished. The remaining 5% task was the integrating process with the car and the drone. Here is the timeline of our group. For each phase, we have different milestones and tasks that are divided to both hardware and software groups. Testing will occur at every end of each milestone to make sure everything works well before implementing with other works. For future works, the next milestone would focus on building and implementing a charging circuit as part of the car-drone integration and making improvement for fully automated hardware system. In terms of website development, statistic and more realistic features are considering to be added for more user-friendly and efficiency. Security and product cycle are also the priorities that we are thinking of implement due to many possibilities and errors that our group have not been able to plan yet. Finally is the budget. Here is the list of components for the car prototype from the 5 million supported from SST. With respect to the drone, from the 15 million disbursement from Schaeffler, the following list of components could be referred to this table, and another 7.5 million disbursement to complete the final prototype of the drone. Here is the reference of our presentation, and that concludes our talk about the automated warehouse inventory scheme project. Thank you for your time.